Okay, so in the number one, we have log of 3x minus 1 equals log of 4 minus x. Now, this problem is very, very similar to other problems we've done where we talked about exponents, where, for instance, if you had 2 to the, watch this, 2 to the 3x minus 1 equals 2 to the 4 minus x, what would we be able to conclude from this? If 2 to the 3x minus 1 should be equal to 2 to the 4 minus x, and it's the same base,
3x minus 1 should equal 4x.
yeah, those two things should be equal to each other. And we already called that make the bases equal, then make the exponents equal. So now you can just conclude that 3x minus 1 is equal to 4 minus x, and away you go doing normal algebra. So in this problem, what we have here, well, first of all, what base is that?
10.
Yeah, they're both base 10 because if nothing's written, it's 10. So we have log base 10 of 3x minus 1 equals log base 10 of 4 minus x. And so through sheer logical force, it must be the case that 3x minus 1 and 4 minus x are the same number. Because otherwise, the two sides of the equation wouldn't be the same. So we can go ahead and just conclude that 3x minus 1 must be equal to 4 minus x. And what we just did was strip away the log part of that problem, and it's just a normal algebra problem now. So as always, you move all of your x's to one side, and then you move all of your numbers to the other side, and finish your algebra, and I got x equals 1.25. And then the question that should immediately come to mind is, we could ask what it looks like. That's another good question. Is that right?
Oh, yeah.
Is it?
Plug it in.
Yeah, plug it in, exactly. If you want to know if something's right or not, plug it in. So 3 times $1.25 is $3.75 minus $1 is $2.75. And then 4 minus $1.25 is $2.75. So without even needing to evaluate that on my calculator, I know that log 2.75 is equal to log 2.75 because it's a tautology. It's obviously a true sentence. Okay, so that's number one. Number two works the same way. I'm going to move sideways a bit here. So number two, we say log base 5 of 18 minus x squared is equal to log base, there's not enough room. That already screen is always cutting me off. 2 log base 5 of 18 minus x squared is equal to log base 5 of 6 minus x. So do you see what we do first?
See if the bases are the same.
Yeah, since it's the same log, the same base, the arguments must be equal to each other. And remember, argument is the vocabulary word we use to describe the input. So we know that 18 minus x squared must be equal to 6 minus x. So we go ahead and we just say that. We say 18 minus x squared is equal to 6 minus x. And now, how do we solve a quadratic, folks? This has nothing to do with logarithms. Whenever you have an x squared term, the first thing you do is
Separate it or isolate it.
you want to get everything to one side. Yeah, whether you push it all to the right or push it all to the left, you want to get everything to one side. This is a negative x squared, so I'm going to go ahead and move everything to the right. So I'm going to add my x squared to the right, and then I'll subtract my 18 to the right. And then I have 0 equals x squared minus 1x minus 12. So recall, whenever you want to solve a quadratic, you have to get all the terms together because that way you have A, B, C. And you could do the quadratic formula, or you could just go ahead and factor. So let's factor this one because it's factorable. What do you multiply to make 12? You add to make 3. Yeah, 4 and 3. So now we have x minus 4, x plus 3, and then what is this called when you have something times something equals 0? Yeah, zero product rule. So now I know that if this times this equals 0, then either this equals 0 or that equals 0. So either x equals 4 or x equals negative 3. So we just wrote down the answer, quote unquote, the answer. So the question we should all be wondering is that correct? So how do you find out if it's correct? You got to plug it in. So I think we can do this off the top of our head. So 18 minus x squared, so 4. 4 squared is 16. 18 minus 16 is 2. So far that's log of 2. And then over here, 6 minus 4 is 2. So log of 2 is log of 2. It really doesn't matter the fact that it's base 5. It's still equal. Okay, now let's plug in -3. -3 squared is 9. 18 minus 9 is 9. So on the left, I have log 9. Then on the right, 6 minus -3
Plus 3.
is 9. So both answers are correct and both answers work. Now you might say, Mr. G, that's kind of a cheap problem because even though there's a log in it, do we really do a logarithm at any point? At any point, did we solve for an exponent? Not really, right? So that was kind of just a problem to be familiar with. Let's take a look at the next couple. Now these are genuine logarithm problems because we are going, well, actually, we're not even going to end up solving for an exponent here either. But we need to know the definitions surrounding a logarithm. So take a look at number 3. We have log base 3 of 7 minus 2x equals 2. Do we have a log on both sides? No, so we can't do what we just did. However, do we have a definition we can apply here? And remember in the past I've said if they give you a log problem, convert it to exponential. If they give you exponential, convert it to log. What did they give us? They gave us a log problem. So we turn it into exponential and it's always left to the right equals middle. So left to the right equals middle. And now look, it's not a log problem at all. It's not an exponential problem at all. It's just basic algebra.
I like how one they did the little arrow thing.
What did they?
Yeah, it's
To show that?
It's like more visible.
Wait, show me how.
So like basically,
Was it like an E?
no, it was just like basically like an arrow like this.
Oh,
So like
okay.
basically you connect 3 to 2 and then obviously the
Like that. So 3 to the power of 2 equals this?
yeah.
Sure, totally works. However you want to think
That's
about
how
it.
I remembered it. I was like,
Okay, we're good. I'm glad that something clicked for you. Okay, so now we'll just finish solving. I'm going to bring the 7 over. So that's 2 equals -2x, dividing out the -2. And so we have x equals -1. Is that correct?
Plug it in.
Yeah, plug it in. -2 times -1 is 2. 7 plus 2 is 9. And is log base 3 of 9 equal to 2? Is log base 3 of 9 equal to 2? Everybody notice you have 2 ways to verify this is true. On the one hand, you can do Emily, 3 to the power of 2 equals 9. Or you could just say 3 to the what equals 9? Good. So yeah, that answer is correct. Okay, now something a little different. Number 5. Wait, did we do number 4? Oh, we didn't do number 4. Number 4 works the same way. In fact, number 4 is very similar. We're saying here log of base 1/2 of 2x minus 1 is equal to -3. So what do we do? Yeah, it's given to in log form, change it to exponential, so that's going to be 1/2 to the -3 equals 2x minus 1. So 1/2 to the -3 equals 2x minus 1. Now notice right here, it's really important that we understand the definition of a negative exponent. What does a negative exponent do, folks? Yeah, it takes the reciprocal. That's really important. If you just know that off the top of your head, a negative exponent means reciprocal. So there's actually 2 instructions right here. It's a negative and it's a 3. So the negative means 2. Yeah, flip it. So it's really just 2 over 1, which is 2. And the 3 means cube it. So that's really 2 cubed equals 2x minus 1, which is 8 equals 2x minus 1. And again, at this point, we're just doing standard algebra. We say 2x equals 9. And divided by 2, we get x equals 1. Folks, I hope you see this algebra. It's wonderful algebra. It's step by step by step by step by step. That's what algebra is supposed to look like. Algebra is supposed to be step by step by step by step, where after every step, you can say what you did. Like from here to here, I converted from log to exponential. From here to here, I did the reciprocal. From here to here, I cubed the 2. From here to here, I added 1 to both sides. From here to here, I divided both sides by 2. That's how algebra should work, is that from one line to the next, you should be able to say one thing that you did.
Right here, we use decimal.
You can use decimals or fractions anyway. Yeah. Okay, number 5. We have natural log of x squared minus 99. Now there's another definition over here I didn't write down. I mean, there's so many definitions, right? We know so many definitions that are important to know in terms of rewriting. So what do we know about your calculator? What does log actually mean? Yeah, that's log base 10. And what does ln actually mean? Yeah, log base e. So what's the first definition we would want to apply?
Log base.
Change it to log base e. Because you need to see the base. You need to see it in order to know how to move forward and what to do next. Okay, so now what? Hector, what do we do next?
First things first, I would need to put that into an exponent.
Yeah, make an exponential for us. So e to 0 equals that. And another definition that we all need to know, x to the power of 0 is 1. Unless, of course, it's 0 to the power of 0, that's undefined. So now we just have 1 equals x squared minus 99. And at this point, we're just doing standard algebra. We have the 99 over. So x squared equals 100. X squared equals size, we get x equals 10 for negative 10. And we immediately wonder,
Which one works? Doesn't?
yeah, do they both work? Does only one of them work? Do neither of them work? Because either of those could be extraneous. We don't know until you plug it in. So if I plug in 10, 10 squared is 100, 100 minus 99 is 1. Is natural log of 1 equal to 0? How could you check? You can plug it into your calculator. You just type in ln 1 and see what it equals. Nadine, does it work?
Yeah.
It does work. Or you can once again use the definition and say log base e of 1 equals 0. Is that true? E to the 0, does it equal 1? Does e to the power of 0 equal 1? Yeah. Okay, so that worked. And then negative 10 squared is 100. 100 minus 99 is 1. Same problem. So they both work. They're both correct.
Because it's true, 99 represents to go by.
Yes. All right, and then the very last one, everybody go ahead and do that one on your own. So number 6, we're going to do log x squared minus 3x equals 1. So consider all the steps that we've been doing. First, you need to identify what that base actually is, and then convert that log to an exponential, simplify it. Since there's an x squared, it's a quadratic, so you want to get all those terms to one side. But probably you can factor it. Maybe put a comma there between the two answers. Because otherwise it looks like you wrote 10 minus 10, which would be 0.
Thank you.
Sure. You can get it over. What is it? Why would it be 0? What's going to be 10 to the power of 1 equals all that? Like over here, we did e to the power of 0. That would be 1. But this one, we're doing 10 to the power of 1, which would be 10. Wait, do you believe me? Okay.
Wait.
Oh, yes.
Okay. It's traveling here. So we have to move this over here.
Well, it's however you want to do it. When you have a quadratic like this, you just need to put all your terms on one side. So it's totally up to you. You can move all the terms to the right. Right.
Okay.
When we say put all the terms on one side, that means the other side is going to equal 0.
Okay.
Yeah. So you can think of it however you want to think of it, so long as all the terms are on one side and the other side is 0. So folks, there's base 10. So we have left to right equals middle. So 10 to the power of 1 equals x squared minus 3x. And so that's just 10. So I'm going to move the 10 to the right since I already have a positive x squared over there. So 0 equals x squared minus 3x minus 10. And then we want to factor that if we can. So what multiplies to make negative 10? 1 and 10, 2 and 5. It has to be a positive times a negative. So yeah, negative 5 plus 2. So then we have 0 equals x plus 2, x minus 5. And so our two solutions by the zero product rule, yeah, -2 and 5. And we immediately wonder, do those work? So we do actually have to check. We have to plug in. So I'm going to plug in -2. -2 squared is 4, and then 4 minus 3 times -2. 4 minus 3 times -2 is really 4 plus 6, which is 10. So is log base 10 of 10 equal to 1? Yes. And again, you should be able to verify that. You can say 10 to the 1 equals 10. That's true. Or 10 to the 1 is 10. 1. So now plug in 5. 5 squared is 25 minus 3 times 5 is 15. That's 10. So once again, you have log base 10 of 10 equal to 1. So either way, both of those answers work. None of your solutions were extraneous. They both work. Okay. Well, I think that's all of those particular types of equations. Now we get to the good stuff. So these last 4 equations represent some real good full diversity of logarithms turning into exponentials and using log properties to solve equations. So let's look at the first one. We have log base 125 of 3x equals 30. What do we do first? Yeah, convert to exponential. So we have 125 to the power of a third equals 3x minus 2 over 2x plus 3. So what definition do we need? What is 125 to the 1/3? 125 to the 1/3 is really x to the 1 over n is really the nth root. So x to the 1/3 is really the third root, the cube root. So we're saying what times itself 3 times should equal 125? 5. Yeah, 5. And this is exactly what I'm hoping that you're familiar with now. If you see 125, you'd say, oh, wait, that's a power of 5. Which power of 5 was that? 5 cubed. And so the cube root of 125 is what number times itself 3 times equals 125? 5. So this is really the cube root of 125, which is really 5. So now we have 5 equals 3x minus 2 over 2x plus 3.
It's 5 at the bottom.
Mm-hmm.
5 on both sides.
When you want to solve for x and x is in the denominator, how do you cancel a denominator? How do you cancel a denominator? Then you multiply both sides by the denominator. That's a general strategy we've been talking about, is canceling things and getting rid of things. So you get rid of the denominator by multiplying top and bottom by that denominator. So that denominator is gone, and we have distributing the 5, 10x plus 15 equals 3x minus 2. And you see in all of these problems, after just a couple steps, we're no longer doing a logarithm problem, we're just doing normal algebra. So what do we do now, Valeria? How do we finish solving this? Well,
Three.
Yeah, for sure, let's move the x's over, and then what? So we have this, and now what do you want to do next? If you brought that over, then you'd have 7x plus 17 equals 0. And with a quadratic, yeah, with a quadratic, you want everything on one side, so you can factor. But right now, you want the x terms on one side.
Okay, so then.
Yeah, there you go. So now you have 7x equals negative 17, and how do you solve for x? There you go. There, so x is negative 17 sevenths. Now, sometimes you just see an answer like that and you feel a little uncomfortable. Like, oh no, is that really the answer? I think I did something wrong. Why would you think you did something wrong?
It's not a solid number.
Yeah, because it's this negative 17 sevenths. So what do you do then? Well, you have to check. So notice, plugging negative 17 sevenths into that looks a little tricky, but I want you all to practice this on your calculator right now. So I'm going to plug negative 17 sevenths in for x, and x, already that thing is a fraction. This is what it would need to look like. First of all, the whole numerator goes inside parentheses, and it'd be 3 times negative 17 sevenths minus 2, parenthesis, that's the numerator, divide by, parenthesis, this is the denominator, 2 parenthesis, negative 17 divided by 7, plus 3, parenthesis, that's the denominator. So everybody try typing that into your calculator, because it requires an incredible amount of parentheses, more than what most people would use. And then they would get it wrong because they didn't use all the parentheses. So what did you get when you typed all that in? 5. Did everyone get 5? Yeah, it would be 5. And so now plugging a 5 in for that whole thing, it's really log base 125 and 5 equals a third. Is that correct? Is 125 to the third equal to 5? Is 125 to the 1/3 equal to 5? Yeah, that was one of the facts we were just talking about. 125 to the power of the third is equal to 5. So yeah, it's true. This is the answer, it works. What do you guys think about all this so far?
A little bit more personal practice.
Yeah.
Oh, you're just saying you would need more practice. Well, sure. Okay, everybody go to practice number 8 then. 6 minus 3, log base 5, plus 2. And let's just agree, what do you think you'd want to do first? Exactly right, you have to isolate the log. That's worth writing down. Isolate the log. We've seen this now many times, that you have to isolate something before you can do something. If you want to solve a square root equation, you have to isolate the root. If you want to solve an exponential equation, you have to isolate the exponential. And if you want to solve a log equation, you have to isolate the log. The -3 is the number in front of the log. And Valeria, thank you for asking. Remember, you can box the thing you want to isolate. This is a log. Not the number in front of it. The log begins with the letter L.
6 times 3 is 3.
What? Oh, you can't do 6 minus 3 is 3. Because that 3 is being multiplied by a
So it would be subtract 6.
Yeah, and then divide by negative. Yeah, there you go. What are you going to do for this? How do you get it to go over? Yes, that's minus, right? Okay. Or where did you? Yeah, the next step would be the order. Right. Is that a negative 2?
Oh, I'm saying. It would be negative 2 over 1.
Yeah. Well, it'd be negative 2 over negative 1, but a negative over negative is yes. Which is just Yeah, that's exactly right. How do you feel about that? Super. Good. Yeah, looks good. That's right, right. Okay. That's right. Meridian. Effort.
I'm over 3. No, I'm reduced that. I'm sometimes 6.
Right, where's your eraser? First of all, we only do one step at a time. So you're only allowed to move over 6.
Okay.
Okay, and then
That's
and now write down what you have. Write down what you have. Good. Okay.
Okay.
Stop. Now parse the log.
Right?
Yeah. Good. Now let's say that whole thing is a number. -3x equals -6. How would you get rid of it?
Oh,
What are those negative x? That's correct. The other way. 25 over 2. All right. So everybody, you can check your work. You would subtract the 6 over, and then you have negative 3 log base 5 2x equals negative 6. And then you can also say it this way. My log is getting multiplied by negative 3, so I divide by negative 3. And then I have my log base 5 of 2x is equal to 2. And now left to the right equals nil. I have 5 squared equals 2x. So 25 equals 2x. I divide up to 2. To get x equals 12.5. You can also write it as 50/4 or 100/8. You can rewrite it any way you like. Okay, wonderful. Emily, Valeria, are you happy with that?
yes.
Okay. All right, now we're about to do a really exciting couple of problems because it utilizes some of the definitions that we learned earlier on. So let's say that you had number 9. And it says log base what? 5? 3. The log base 3 of x minus 4 plus log base 3 of x plus 4 equals 2.
It's going to be.
Well, hold on. So folks, I can't emphasize this enough. This whole metaphor or analogy, not analogy, framework of thinking about rewriting something, okay? That's just rewriting something itself. There's so much power. So right now I'm adding 2 logs together. And I've got an x in both of them, and I'm wondering what to do. So you'd say to yourself, gosh, is there some way to rewrite this whole problem? Is there some way to rewrite a log plus a log? So is there some way to rewrite a log plus a log? What is the definition we learned? Yeah, that if you have a log plus a log, you can rewrite it as a single log of the 2 arguments being multiplied together. So again, it's just so important that you've got all this stuff floating around in your mind, or better yet, written down on a sheet of paper. And at any given moment, you're like, gosh, what can I do to this? What could I do? How could I rewrite this? And you just go look at your formula sheet until you find something. You're like, ooh, I could try that. So then you try it. You say, okay, I'm adding 2 logs, so that would be log base 3 of x minus 4 times x plus 4. And I can't emphasize enough, but again, as a mathematician, so much of what you do, you bumble around in the dark and you try things until one of them works. Because we're not born with an intuitive knowledge of how to move through problems, right? What we're born with is the ability to try things. That's about it. That's what babies do. My baby, he's 8 months old. He wanders over to something. He's like, interesting. Puts it in his mouth. Picks something else up. Interesting. Puts it in his mouth. I mean, that's what we're born to do is try things. But what you need is a list of things to try. And then you just try things until you get it. Okay, so now what do we do? Combine? Oh, you mean like multiply those? Yeah, by all means, go for it. This is a conjugate being multiplied by a conjugate, so we can multiply, FOIL it out. What do you get? Yeah, that's going to be x squared minus 16. What else can we do? Huh? Put it in exponential form. This is log form, but in exponential form. So 3 to the power of 2 equals that. So 3 squared equals x squared minus 16. You know, another thought for you is maybe we spend too much of our time in math asking the question, what should I do next? That's a tough question. What should I do next? It requires you to have the mind of God. I don't know what I should do next. How about we ask the question, what could I do next? What is something I could do? Right? That's all you really need to ask is what could I do next? You know, so like right here, we multiplied that together. And then here we could convert it to exponential, and we did. So now we have 9 equals x squared minus 16. And at this point, we're practically done. It's just normal algebra. Add the 16 over. So x squared equals 25. Then square rooting, we get 5 or -5. And then, of course, the question is, do they work? Do they both work? So let's find out. I'm going to try the positive 5 first. So that would be log of 5 minus 4 is 1, plus log of 5 plus 4 is 9, and theoretically that's equal to 2. These are both base 3. So now you actually have to look at each of those and solve it. So 3 to the what is 1? 3 to the what is
0.
1. Yeah, 0. 3 to the 0 is 1. And then 3 to the what is 9? 2. And is 0 plus 2, 2? Great. So that one works. How about -5? I plug in -5. That'd be log of -5 minus 4 is -9. And log of -5 plus 4 is -1. And that equals 2. Now notice this is deceptive. There's a 1 and a 9 and a 1 and a 9. So you might look at that and be like, boom, same thing. Done. It works. What's the log of -9? 3 to the what is -9?
It's not real.
Yeah, it's not real. This is a domain error. One of the things we learned about logs is you can't log 0 and you can't log a negative. Because the graph 3 to the x looks like this. And it's never going to get all the way down here at -9. Unless you really tried. No, even then, it's never going to get down there to -9. So this is false. And therefore, -5 is extraneous. All right. Well, that was a really exciting problem. Just look at how many definitions we used. We used the definition that a log plus a log is the product of the arguments. We used the definition of FOIL to get a difference of squares. We used the definition of converting a log to exponential. And then we did a square root, which is plus and minus. That's a lot of definitions. Okay?
If we had another x term in there, then we do the quadratic. Or,
yeah.
But because we don't.
Yeah, because it wasn't, we didn't.
Okay.
Yeah. Really nice, folks. So, what in number 10, which is actually number 12, I guess I got rid of some problems. Number 12, natural log x plus 1 minus natural log of x equals 3. Big question, not what should you do, what could you do? Yeah, you can view it as a division problem. That this is really log minus log. We have a formula for that. And so we can turn that into natural log of x plus 1 over x. And notice that's very helpful because now we just have one log. What's another definition we can apply?
Log.
Yeah, ln is log base e. So now we have log base e of x plus 1 over x equals 3. What's the next thing we could do? What's another definition we can do? Yeah, just convert it to exponential. So now we have e cubed equals x plus 1 over x. Now, folks, this is where it gets a little hairy. You look at e cubed and you're like, that's 2.7 cubed. That comes out to some weird decimal, like 24 point something, something, something. And look, having that e cubed there, it can so trick your brain into thinking that this is hard that you don't do what you would naturally do if it were a whole number. So I want everyone to think now about what you would do if this problem was just 5 equals x plus 1 over x. This is a really good problem-solving strategy. If you're feeling baffled by what you're looking at, try something easier and see what you would do. So what would I do right now to solve for x?
Multiply x.
We're going to multiply by the denominator on both sides, right, to cancel that out. So now I have 5x equals x plus 1. Okay, then what would we do? Yeah, we subtract it. That's really a 1x. Now watch very carefully here. I'm going to subtract 1x. Now everyone in the room, you would just do 5x minus 1x is 4x. And you would write down 4x equals 1. And then you divide up the 4 and you'd be done, right? But notice, what if I just wrote down 5x minus 1x? I mean, I don't think anybody would do that. That wouldn't be normal. But you could, right? You could. And then what could I do here now? Could I factor out an x?
Yeah.
And then what would I have?
X.
That. I'm factoring out the x. And if I wanted to get x by itself, x is being multiplied by this parenthesis, so I would divide by the parenthesis. Now, looking at what I just did here, that might seem a little weird, like, this, gee, come on, man, that's 1 over 4. Why did you do that? But sometimes you do that to get yourself ready to do something a little strange, you know, because now we have an e cubed. So let's do the exact same strategy. What's the first thing we do? Then we're going to multiply off the x, right? And so now that gives us e cubed x equals 1x plus 1. And again, seeing that e cubed x, it might feel weird, might feel uncomfortable, but it's still just e cubed is just a number, 24 something. Okay, so then what did we do?
Brought the 1x over.
We subtract 1x from both sides. And again, we can't really subtract e cubed minus 1, but I can just write it down. Right? This is good to see. So, if you don't know what to do with something, just write it down. Now what can I do?
Factor out the x.
Yeah, factor out the x, and now I have x outside of e cubed minus 1. And again, I want to solve for x.
So divide.
Yeah, and so you divide by e cubed minus 1. It looks crazy. It looks weird, but is it the correct answer?
Yeah.
We think. We don't know yet. We sure hope it is. So now here's another fun, clever strategy. We came up with this answer called x equals 1 over e cubed minus 1. Now, first of all, what number does that represent? Could you call up Pizza Hut and say, hey, I'd like to order 1 over e cubed minus 1 pizzas? Could you go to Home Depot and say, I need a piece of wood that's 1 over e cubed minus 1 feet long? That'd be silly, right? So instead, what would you do? Yeah, so 1 divided, now everybody try this. This is 1 divided by parenthesis e caret 3 minus 1. Type that into your calculator. And notice that your calculator will automatically give you a parenthesis after e caret parenthesis. You got to close that parenthesis. Otherwise, it thinks you're doing e to the power of 3 minus 1, as opposed to e to the power of 3 minus 1. So you need the parentheses correct. Everybody try it. Man, there could be a whole class on just how to type things in your calculator. Oh, wait, I think that's called a regular math class. Okay, what did everyone get?
0.0523.
Yeah, x equals 0.0523956965. Dot, 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 dot. And there's really infinitely many decimals, right? So the answer, is the answer actually 0.0523956965? No, because there's more decimals. And now if I wanted to just approximate, could I say the answer is 0.0524? Yeah. Is that the real answer? No. Okay, so now, what if I had the full answer with all the decimals? What would happen if I plugged it in there and subtracted? What answer would I get? Should equal 3. But I'm not going to plug in all infinitely many decimals. I'm just going to plug in a number that's close to the real answer. So if I plug it in, what should I get? Something close to 3, right? So if I plug in, if you plug in, you're all about to, if you plug in at 0.0524, which is a number close to the answer, into here and here and subtract, you should get a number close to 3. And that would give you confidence that you did it right. So let's all try it. If you plug in 0.0524, that's going to be natural log of 0.0524 plus 1, which is 1.0524. Minus natural log of 0.0524. And it should be close to 3. If we're choosing an answer close to the real answer, then it should give us a number close to 3.
It's kind of like my answer, my answer is my almost answer.
Yeah. Yeah, my almost answer is the almost answer. Yeah, now you might say, Mr. G, what's happening right now? This is sloppy. What does this even mean? But this is a valid mathematical approach to see if your answer is correct. Because what if instead of doing 0.0524, what if I kept more decimals? In fact, if you want to have a little fun, what if you kept all the decimals that they gave? 1.0523956,965, which nobody would do because nobody wants to write it down. I don't know how in our culture we're so averse to writing things down. Like it's going to break our hands or something. All right. So now if I plug that in, I mean, what's the worst thing about writing all that down? I have to type it all in. Again, our culture, we don't want to do things. So I type all that in, and I subtract natural log of all that again. 1.0523965. It actually gave me 3. It gave me 3 on the dot. Now that's a rounding error, folks. It's not actually 3. If you actually had that in the Google calculator, it would probably give you 2.99999. And it would give you so many 9s that the calculator would experience overflow. That is, it had more 9s than the calculator had. and it would just assume to round it up to 3. So that is a calculator error, even though it's a convenient calculator error, because it makes us think that we got the right answer, which we did get the right answer. All right. Well, folks, you can expect to see some problems like those. All the problems that we just did are really good log problems. So what questions would you like before we do some application problems?
But earlier, what input did you use? I keep hearing a different answer.
What's that?
I keep hearing a different answer.
What input did I use for?
Yeah, for the
This thing?
yeah.
When I did 1 over e cubed? Or when I plugged it in here?
You put it through.
Right, but are you asking how to do 1 divided by parenthesis e? Where's e? Yeah, there's an e. Oops. No, okay. So 1 divided by parenthesis e divided by, so there it is, e cubed. Exclude. So first of all, that's the decimal, 0.0523.
Oh, then I put it on that. Put it on.
Oh, okay. Yeah, so is that. All right. So folks, we've accomplished a lot. Honestly, truly, in just a couple of days, this is a lot to accomplish. I barely have written all the formulas that we did up here, but we've done a lot in terms of understanding that we're trying to solve for an exponent, and to do that, we invented this terminology called a logarithm, which your calculator knows how to compute. And then using that, we have all these ways to rewrite things such that we can go about getting an answer. So now that we have all this theory under our belt, the real question is, why would I ever need to solve for an exponent anyway? All right, let's go back to the original question. Why would I need to solve for an exponent? Why would I need to solve for an exponent? In real life, why would I need to solve for an exponent? So for instance, I started us off with a problem like this, 2 to the x equals 50. Well, I mean, that's interesting and all. I mean, I can sandwich that and say 2 to the 5th, 2, 4, 8, 16, 32 is 32. And so 2 to the x is 50, and 2 to the 6th is 64. So we can make a sandwich and say the answer should be 2 to the 5.5. But who's really sitting around wondering 2 to the what is 50? So can you think of any real life application problems where you'd need to solve for an exponent?
Yeah. Yeah.
Oh, great. What?
If you're a mathematician.
Wonderful. Yep. Nailed it. Nailed it. Okay. What's another example? When would you need to solve for an exponent?
Finance.
What?
Finances.
Finance, that is correct. And maybe that's because you see right up there on the board that we're about to talk about interest. The real question is, what are some formulas that actually have exponents in them? And all of you know at least one formula that has an exponent in it, and that's the formula for compound interest. A equals P, 1 plus R over N to the N T. So folks, that's the formula for compound interest. Okay. Simple interest is simple. It's just PRT. Principal times interest rate times time.
I was thinking of another one. It would be a physics one.
Okay, what?
I was trying to remember it, but it was something.
E equals MC.
MC squared has an exponent, but it's 2. It's not a variable.
Something velocity squared, I think. I can't think of it right now.
Okay. There are lots of physics equations that have variables in the exponents. Okay, so everyone, let's just look at this real quick and understand what this formula is saying. Okay, P is your what? P represents principal. It's your principal that you invest. Principal is the amount you invest. So, let's just say, just for fun, we're going to say that we invest $1,000. Okay? So what is A? The amount you have when?
You do when everything's been done.
Yeah, exactly. The amount you have at the end. Okay, so you invest some money, and then when all is said and done, they give you some money back. And hopefully, it's more. It's the least how much you gave them, preferably more, and how much more, and that's how much interest you earn. Okay, what's R? Yeah, that's your interest rate. And even though every interest rate in the world is expressed as a percentage, like 5% interest, we never actually compute with a decimal. You have to turn it into a decimal. Sorry, we never compute with a percent. You compute with a decimal. So to do a decimal, you move the decimal twice to the left, right? So that's really 0.05. So the rate is always a decimal, and you move the decimal twice to the left to convert from a percent to a decimal. Okay, next variable, n. What is that? A good guess? No. Noodles?
Your neck.
Thanks for you.
Nincompoop? Yes, it is times per year. N is the number of compoundings per year. That begs the question, what's a compounding?
Annual, monthly, bi-weekly.
All those words are correct. Compounding means the number of times per year they give you interest. Okay, so for most accounts, they give you interest once a year. You leave the money in the account, they give you some interest at the end of the year. So a compounding means the number of times they give you interest. Now we might as well discuss some of those, but we'll do that in a second off to the right. So that's n. The last variable is t. T represents time. In what unit? Years. Always years. Time is never months, days, or anything like that. They might tell it to you in days or months, but you have to convert it into years. Just like you're taking a percent and you convert it to a decimal. Okay, so we have all these parts and pieces.
Actually, I have a question. So let's see. If my rate, let's say my rate is the same, my net would be weekly, and my time would be 6 months.
Okay.
And that's how, and like, well, how much would that be in the end?
Well, first of all, if you're saying 6 months, t would be 0.5 because it's half a year. And then weekly, so the number of times per year is 52. So n would be 52. And then rate was, yeah, 0.05. Yeah. Okay, so while we're here, let's go ahead and talk about n. So if n equals 1, that's 1 time per year, we call that yearly. If n equals 2, that's 2 times per year. I think we call that semi-annual. And by the way, instead of calling it yearly, you could also call it annual interest. That's what that means. There we go. If n equals 3, nobody does that.
Yeah, you don't call it your anniversary.
Yeah, there's no triannually or anything like that. 4, we do, and that's quarterly. 5, nobody does. We don't have a word for it. 6, we do. 6 times a year would be it's every 2 months. Now, is that bi-monthly or is that semi-monthly? I believe the terrible news is that both words are used interchangeably and you need context to know what they're saying. So, but I think it's either or. Even though semi-annually is definitely twice a year, biannually means every other year. Okay, but bi-monthly and semi-monthly both mean every 2 months. Although bi-monthly can also mean twice a month. It's terrible. It's terrible, folks. But yeah, they're just terrible. You should say every 2 months rather than messing around with that. Okay, there's no n equals 7, 8, 9, 10, 11, 12. What's n equal 12 times a year would be monthly. Now, do we have more than 12? Somebody already said 52. So that would be weekly. What's the number bigger? 64. 64? Oh.
Oh, no, I was thinking 64, but I don't know why.
Yeah, 365 would be daily. Now, beyond that, we enter.
Daylight saving time.
Well, daylight saving time affects hours in the day. Actually, it just affects time. You could say leap year, which changes to 366. Yeah. Okay. So what's more than daily? If you were going to get interest more than once a day, it'd probably be hourly. So I take 365 times 60, and then that would be 21,900 times a year, and that would be hourly. Nope, did that wrong. Times 60. I want to do times 24. 365 times 24. There we go. 8,760 times a year would be hourly. Again, that'd be awesome if I had an interest-bearing account that every hour I was like, just made some interest. Bing, just made some interest. Right, yeah, it does. Okay, so what about beyond hourly? What's even shorter than an hour? A minute. Now
$5 pennies an hour.
times 60, so now 525,600. So imagine every minute you get some interest. That'd be cool. What's even shorter than a minute? Seconds. Whoa, now I want this deal. 315,306. No, 315,360,000. Okay, that'd be second.
So that's something like Jeff Bezos or
And there's
Bill
nanoseconds.
Gates.
What?
Don't they get like something ridiculous?
What, like milliseconds or something?
Or,
Nanoseconds.
like I'm pretty sure they get. I think it's either a minute or
Who?
Bill Gates or Jeff Bezos. Or
Oh yeah, sure. I mean, you can calculate how much money they're making every second, sure. Because if you just take like something normal, like $50,000 a year, like just for fun, $50,000 per year, divide that by 365, that's per day. So this is per day. And then divide by 24 hours in the day, that's per hour. So per hour, right there, or per minute would be 10 cents, or per second, well, that's unfortunate. It's a fifth of a penny. So that's how much a normal, quote unquote, person is making per second, right? That's what I said. So this was a dime per minute. This was per hour. Yeah. So probably Bill Gates and those guys are making a whole lot of money per second. Okay. What did I want to say about all this? What if we go ahead and let n equal infinity? This is an interesting concept. Because here, even secondly, what happens is, imagine that you have a sink faucet and just drips one drip of water every second. Okay, so it goes drip, drip, drip. Well, what if instead of dripping, where it's a discrete raindrop of water that drips, if it's just a flow of water? Okay, that's what this is. If n equals infinity, you're saying that the water is constantly flowing. It's not dripping. It's just flowing. And it doesn't mean that you turn the bathtub on full blast and you got this roar of water. It's just a thin stream of water continually flowing and putting water into your bathtub or putting interest into your bank account. When n equals infinity, we no longer use this formula, which is the regular compound interest formula. We use A equals P e to the RT. And we call that continuous interest. Continuous, like a stream of water. So those are your options for n. When we talk about the number of times it's compounded per year, we're talking about how many times a year they give you interest. And as n approaches infinity, you just have a different formula to use. Because it's rather unwieldy to divide by a billion and then raise it to the power of a billion. Instead, this formula becomes this formula, where e is the normal number e that we've been talking about, which is why your calculator has a log base e number. Because there are applications where e is the natural number, natural logarithm, natural number that comes up. All right. All that said, folks, let's do one simple, getting us in the mood question. Let's say that I wanted to invest $1,000 at 5% interest for n equals 12. I'm just going to choose n equals 12. And I would like to know, how long do I have to wait to double my money? So how long do I have to wait to double my money? Well, if I want to double my money, how much should I have at the end? 2,000. So now look real quick. If I plug all this information in, the amount, okay, I'm going to write above each other so you all clearly see. This is like the big payoff here, okay? We spent 3 days talking about this so that we can all do this. 2,000 equals 1,000. 1 plus 0.05 over 12 to the 12 times t. You see that variable t? We want to solve for t, right? I just said, how long do I have to wait to double my money? Where is t?
Yeah, x.
In the exponent. That's what we've been building towards, is the ability to solve for a variable in the exponent, and now we can. So right now, we could solve how long until my money is doubled. And I'm going to actually solve it for you here. So 2,000 equals 1,000, 1 plus all that, and then 12t. Oh, I'm sorry. If you don't mind, I'm going to change that to 3% interest. That's more like our economy right now anyway, and it divides more cleanly. So 3% interest. Glad you like that, Lee. So then I'm going to simplify this. 0.03 divided by 12. So that's 2,000 equals 1,000. 1.0025, all to the power of 12t. I'm going to divide off the 1,000, so that's 2 equals 1.0025 to the power of 12t. Notice this 2 right here, folks, is not an accident. I asked how long until I double my money. That's the number 2 right there. If I had asked how long until I triple my money, what would that number have been? A 3. Okay, so now I have this. I'm going to rewrite it with my exponential on the left because I'm more comfortable with my exponential on my left and my answer on the right. So now I'm going to take that and convert it to log form. So now I have log base 1.0025 of 2 equals 12t. So there, I'm using a logarithm to solve for a variable in the exponent. This, I use the change of base rule, and I say log 2 divided by log 1.0025, because now my calculator can solve it. And right here I have 12t. Keep in mind, I could divide off the 12, but that might look awkward. I'll just multiply both sides times 1/12. Why would I multiply times 1/12? Because it cancels the 12, giving me t. And over here I have the very nice answer, log 2 over 12 log 1.0025. So that's my answer. I'm going to type it in my calculator. Everyone watch very closely. To put this in your calculator, you need a parenthesis around the numerator, a parenthesis around the denominator, and your calculator will automatically put a parenthesis around each argument. So it should look like this. Parenthesis, log, parenthesis 2, parenthesis, parenthesis, divided by parenthesis 12. Log, parenthesis, 1.0025, parenthesis, parenthesis. A lot of parentheses, folks. So log 2 divided by 12 log 1.0025. And the answer is t equals 23 years. What does that tell us? If you have $1,000 and you want $2,000, get a job. Right? Because waiting 23 years to make $1,000, you can make $1,000 in a month. You just go work any job.
What would you do would you increase the rate of interest?
You would need to get a higher interest rate, or you would want more compoundings, or you'd want a larger principal. Well, yeah, the larger interest rate.
Is there any way to how would you apply this to a 401k, I guess?
401ks are not an interest-bearing account. It's the stock market. The stock market is at the whimsy of public demand and supply. The stock market just follows the market. So there's a historical trend that the stock market gets an average return of anywhere from 6 to 10% per year. If you look historically, you have gains over time, but it's not guaranteed. And it's only over the long run. If you're going to put your money in the stock market, you should agree to put it there for at least 20 or 30 years. Because that way, even if there's a recession or what do you call it?
For the national thing.
Yeah, national emergency. What do you call it? It's a recession. It's not the Great Depression. We called something else in 2008, 2009. What did we call it? The Great Recession. Great Depression.
No,
Was it like something with Bush?
no, we're talking about the housing market.
Yeah, the housing market. I thought we called it something. It was an unfortunate event in any
Was it
case.
great
A lot of people lost
great
money.
housing scandal?
Yeah.
Oh, when the other dropped, like,
Yeah, maybe it's just recession. Yeah, Great Recession, not Great Depression.
Isn't there another one coming up soon?
There will always be another one. All right. Okay, folks, this is a good place to stop. We just saw a nice example. First, that this is a formula that's very important. It'll definitely be on your test. We saw what n represents. We saw how to plug everything in, and we saw how to solve for a variable in the exponent using logs. And notice that we used everything. We used converting an exponential to a logarithmic. We used the change of base formula, and then we got our answer. So this is really what we were leading up to. So the time is now 1:38. Let's be back at 1:48, and then we'll go, and we'll finish the rest of our word problems.
So Mr. G, I heard from someone that the best financial decision you could make at a young age would be to invest any money you had into a 401k.
Yeah, exactly right. Because a 401k is based on the market, and the market does have proven returns over the long term.
Good question. Should I just wait till the end of class?
No, show me again right now.
So I got So quadratic formula.
Yeah, and then you get 2 decimals for that? Go and get 2 decimals for that.
So would I do 6 plus 18 divided by 16?
And then 6 minus 18 over 16.
And then I can just do it on my calculator.
Uh-huh.
Okay. And then this one right here. Finding which one was extraneous.
Yeah, which one is extraneous? Oh, okay, we'll go do it.
Yeah, I'll do
Okay.
that real quick.
Alright.
Another quick question. So for the quadratic formula, would I plug both of those in to see which one's extraneous for that?
Right.
Okay.
Well, no, that one,
Oh,
the answers
that's
are going to work.
the x. That's both x's.
Yeah, whenever you factor a polynomial, those are not going to turn out to be extraneous.
Okay, because they both are.
Yeah.
Okay.
But see, I feel like a jerk just saying that because, like, how do I know that those aren't going to be extraneous, but the other one is going to be extraneous? But here's the difference. In the polynomial, you factored it.
Yeah.
It wasn't an equation set equal to something, and then you were solving the equation. You were merely factoring, and factoring is rewriting. So the rewriting is the same as the original. Whereas when you solve an equation, that's an equation that's set equal to 0, and you're finding a number that you can plug in. And sometimes the algebra leads you to a number that when you plug it in is a domain error, which the equation doesn't really have knowledge about its own domain, right? It's just an equation. So sometimes when you do algebra on an equation, you get an answer that doesn't actually work. But with a polynomial, you're just factoring. It's not an equation. Does that make sense?
Yeah.
Okay. I really was trying not to do like because I say so.
Right. Yeah.
But really though, because I say so.